Okay, well, hopefully you have now taken a break from the first part of these chapter 2 notes, where we were dealing with issues related to theory building in psychology, and the difficulty in developing theories about things we can't really observe. And that, as we know, is called the construct versus variable problem. We can observe and measure variables, but we are always concerned with how well those variables measure the construct that we are really trying to study, which depends quite a bit on how we even define the construct. And so then we also then have to worry about the validity of our measures. But as I had mentioned at the end of the last video, we are going to proceed under the assumption that our measures are now valid, which of course it remains in real life a concern, but we're going to move on and talk about, now that we have decided on our appropriate measures and variables and what we're going to study, how do we appropriately design an experiment? And this is where we talk about hypothesis testing, because our goal from before is that a real, true scientific theory should generate predictions. And those predictions should come in the form of a hypothesis, which we might state as an if-then kind of statement, right? If X, then Y. And what should also be hopefully clear from that kind of if-then logic is that this is meant to establish cause and effect relationships between variables. So if I say if X, then Y, I'm implying that I think that X causes Y to happen. And that's really one of the major goals in all scientific research, is to establish our ability to claim certain cause and effect relationships exist in nature. And in psychology, what we're trying to do, of course, is that we want to understand human behavior. And therefore, we want to understand what actually causes human behavior, what causes a person to do what they do. And I can have a theory about that, but in order to test the theory, I need to be able to generate a prediction that can be tested. And that means that I should be able to demonstrate some causality of behavior in an actual study. So for example, let's think about a theory first, a theory about human behavior that has something to do with helping others. And I might think, for example, or let me be a little bit more broad than that. Let me talk about our social behaviors, broadly speaking. That is, any action that we engage in the presence of other people, where other people will be able to observe us. And I might have a theory that says something, for example, that people do not like to be seen as foolish in front of others. They don't want other people to think that they are foolish. They don't want other people to think badly about them for whatever various reasons. Right? That's a very broad general statement. It could be a theory. But how would I test that? And one way to test it is to come up with a situation where a person has an opportunity to act in public, to do something in the presence of other people, and to determine whether or not their behavior might be influenced by the presence of other people. And I'm talking here about this first one about bystanders and helping. I mentioned about helping others. Why am I thinking like this? Well, one possibility, again, this goes back, by the way, to when we were talking in the earlier part of the notes about making observations that lead to theories. And these observations began in the mid-20th century because there were some stories that were kind of like memes in a way, really, for, you know, from newspaper stories and things passed by word of mouth. One was an infamous story about a woman who in, I believe it was New York City, who was murdered on the street, quite unfortunately. And the story goes that there were people who were in their apartment buildings who heard her screams for help and didn't do anything, and didn't call for the police or didn't assist or intervene or anything like that. And so she was essentially kind of murdered in public, and no one did anything to help her. And this led a lot of people to speculate about why people would do that. And there was all kinds of speculations about how people just don't care anymore, or something about living in these kinds of densely populated urban environments that causes us to care less about our fellow humans compared to people who may live in more rural environments. All these kinds of things were bandied about, and psychologists came up with this idea that maybe it has something to do with what we call social loafing. And the idea behind social loafing is the assumption that it's not my responsibility to help here because someone else will do it. There's hundreds of other people who are watching this happen, and someone's going to take care of it, therefore I don't have to. But of course, if everyone is thinking that, then that might mean that nobody will help, right? And that's one possible explanation. Another possible explanation is what I was saying earlier about a fear of appearing foolish, right? Because you might think, for example, in the case of the woman who was attacked, maybe it was a pretty unambiguous kind of situation, maybe. But there might be sometimes situations where we might think, I'm not too sure if this person needs my help or not, right? And you don't want to necessarily try to offer help, try to do something, and then be told, hey, what are you doing? Leave me alone, right? And then you feel embarrassed. And if there's lots of other people standing around, now you feel extra embarrassed because of all of the people who might think you're weird or foolish for some reason. So these are the kinds of theoretical, interpretive, speculative kinds of statements to explain human behavior. None of them are necessarily scientific in and of themselves, right? This is just what we might call naive psychology or folk psychology, because we can sit around all night long and think about why people do these kinds of things, right? That's not scientific. But if we could formulate one of these theories into a prediction and test it, then we could say that speculation might become more of a scientific theory, because now it's attempting to account for, if we go back to our definitions of a scientific theory, it's attempting to account for the observations that we have made, and it's attempting to make some predictions that could be tested. So the argument here, maybe let's go back to the social loafing idea, is that with social loafing, the idea is that if there's only one bystander, then that person knows that there's no one else there to help except for themselves, right? That person is the witness who can help, and there's no one else to do the helping. So we would predict there would be no social loafing happening there. Another phrase that's used, by the way, is called diffusion of responsibility, right? The responsibility to help has now been diffused across all of the people who are watching. But if there's only just one person, there's no diffusion to occur, right? But if there's a second person now standing by, there could be a little bit of diffusion, but maybe it's less. And so the odds that one of those two people would help is maybe still relatively high. But if there's 10 bystanders now, that responsibility gets diffused across 10 people. And now the odds that any one person will help might be low. We could even state it as in terms of a proportion of how many people. So it goes from being when there's only one person there, a 100% chance, to when two people are there, a 50% chance, to when 10 people are there, now it becomes only a 10% chance that any one person will help, right? And so you can start to see how there's a more systematic kind of prediction that's being made here, to up to the point where we could say that if there are 100 bystanders here, now there's only a 1% chance that any one of them will help. And so that's a much more clearly stated prediction in terms of cause and effect, that as if I increase the number of bystanders, the odds that a single person will offer help in a given situation will decline, right? So I'm making this a cause and effect statement broadly written here on the slide, as the presence of bystanders is what causes someone to not help someone else, right? But in order to test this statement, I need to be able to do the experiment. I need to test it. And so what we need to do here is we need to think about what we think is the cause and what we think is the effect. And those have technical names in the research method. So what we think is the cause is called the independent variable. And what we think is the effect is the dependent variable. So in this case, presence of bystanders is the cause. That's an independent variable. And the helping behavior, whether or not someone helps, is the dependent variable. So in order to claim a cause and effect, if then kind of statement, what we have to do is we have to manipulate the independent variable and then observe whether our manipulations to the independent variable cause the expected changes to the dependent variable. So in this case, we manipulate the number of bystanders from just the one person to 10 to 100, who knows, whatever it is you think you need to do here. And then you observe corresponding changes to the dependent variable. So as you continue to increase the number of bystanders, does this statistically decrease the helping behavior just as we have previously predicted? But one of the things that we have to be concerned about here is that those two variables, what we're trying to do is we're trying to isolate the relationship between these two variables here. I really want to study the relationship between the number of bystanders and helping behavior, right? The IV and the DV for short. But I have to also realize that the world is not that simple, and that the presence of bystanders and how many bystanders are present, while that might play a role in someone's likelihood of helping, and therefore is an important factor in the cause of their behavior, it's likely to not be the only cause of their behavior. And so in order for me to study this relationship, what I need to do is I need to isolate that relationship to the exclusion of other things that might actually be influencing that person's behavior, because I'm not interested in those things, at least not in this current experiment, right? In another experiment, we can look at those things. But in order to do this, we have to be able to isolate individualized relationships between variables. And if we find that in a given experiment that variable has no effect, like the independent variable that we think is important actually has no effect, then we can push that aside and say, okay, we've ruled that one out. Now let's take a look at another variable, and we can start sorting through different variables and study them in isolation. And that's a fairly simplistic way of maybe studying psychology. But it's an important way to start, because we have to figure out which variables are relevant and which ones are not. And then later, we might try to study combinations of variables, because it might be the case that they interact with each other in unusual and unexpected ways. And we would want to know that too. But we have to get started somewhere, and that is through the simpler cases of isolating relationships between independent variables and dependent variables. So in this case, it's about the number of bystanders and helping behaviors. And that means that we want to think about what are the other things in the situation that could have some effect on helping behavior. Is there something about the person who needs your help, right? Because what's going to happen here is that I'm going to have to set up a situation. I'm going to have to set up a manipulation of some sort in a laboratory. What am I going to do? How could I do this study in the first place? Well, one possibility is, well, one thing we have to keep in mind here is that if I bring a participant into the laboratory and I tell them, you are here today because I want to study whether or not you're going to help someone who needs your help. And so we're going to walk out of the building here and you're going to see someone who needs help, and I'm going to determine whether or not you will or will not help them just by observing you. And then of course we walk outside of the building and there's somebody who has fallen down. And what is that participant going to do? Well, I don't know what they're going to do at this point, because I have told them already what it is I'm trying to study. And by doing that, I have done several things. One is that I have told them what my expectations are for them. Two, I have now placed kind of a little bit of a spotlight on them. They know that they're being observed and tested on their helping behavior, and that's going to make them self-conscious about any social judgments that I might make about them or that anyone else might make about them. And three, they're aware that this whole thing is a setup, and that the person who they observe having fallen down is probably an actor of some sort who's probably not really hurt at all. So there's all these weird things going on that I have to control for, right? I need to make sure that those kinds of thought processes from the participant their thought as to why they're being tested, what this experiment is about, and how serious and real is the emergency that this other person is having. Is it really, right? So those would be extraneous variables that I would have to be concerned about, right? So I'm going to have to do something that we call deception, right? I'm going to have to bring my participant into the laboratory and effectively lie to them. I'm going to have to say, well, we're here for something else. Maybe I can say it's a visual perception experiment, and I'm going to first thing I'm going to do is I'm going to have them in the room, and I'm going to give them a simple little vision test to measure their visual acuity. Right? Read the eye chart, and I'm going to tell them that this is just simply to make sure that your vision is normal before we go do the actual visual perception experiment, which is in another room. So they do the vision test, and they say, okay, now here's what I want you to do. I want you to go out this door, and I want you to walk down the hallway to some other room and go into that room, and my assistant is waiting for you there who will continue the second part of the experiment. And I send them on their way down the hallway. Meanwhile, of course, this is not what the experiment's about. Maybe what's going to happen is that I have an actor, and an actor who is part of an experiment is actually called a confederate. So this is a person who is not really who is not really just a coincidental bystander, right? That they're actually trying to do something to manipulate the situation. So in this case, my confederate is walking down the hallway, the opposite direction as the participants. So they're coming down towards the room that the participant has left, and they're going to pass each other. And at some point, some predetermined point, the confederate is going to drop their papers or their books and act a little exasperated. They're in the middle of the hallway. And we might be concerned, will our participant stop and help? Offer to help pick up the papers and the books that have fallen? Or will they just walk right on past? And of course, what I could do to manipulate the situation is to manipulate how many other bystanders are there. Is it just the two of them together, in which case there's just the one person, my subject? Or is there a second person? Are there 10 people? How many people are all there? And is it possible that as I keep increasing the number of people who happen to be around in the hallway, that, and again, all of these bystanders are actually just confederates that I have hired to be there just at that moment, right? So that's my manipulation. I'm manipulating how many people are there. And I'm going to observe if that person helps or not. And so, of course, I will do this with a bunch of different participants, right? I'm going to maybe bring in 100 participants and send them down the hallway. And some participants will experience no bystanders, and some will experience many bystanders, and some will experience some in between number of bystanders, right? And what I can do is, after I've done that with a bunch of participants, I will be able to calculate what was the total number. So let's just say, for example, if 25 participants experienced the no bystander situation, what percentage of that 25 actually stopped to help? And if there were another 25 people who experienced, let's say 15 bystanders, what was the total percentage of that group that actually stopped to help? And I would probably expect to see that the rate of helping was lower when for the group of people who had the greater number of bystanders. But again, that's only if I manage to control for all of those things that I worry about might influence what the subject is thinking about the whole purpose of this experiment. And so if I manage to fool them so that they don't believe that they're being observed for this purpose, that they might be more apt to act naturally, which is crucial here, right? But there might be other things. For example, let's think about my confederates. What if on the day that which I'm doing the no bystander conditions, my research assistant, who is the confederate, is person A. I'm just going to describe them generically, person A. But on a different time, a different day, different week, when I'm doing the other version of the experiment, when there's lots of bystanders present, person A is not available to help me, so I hire person B to help me. And so now it's a completely different confederate who is dropping their books and papers and acting exasperated. Is there something about person A versus person B that might make our participants more or less likely to help them? Is there, so let's give some examples here. If one of these persons is a man or a woman, my subjects are also going to be men and women too. So are you more or less likely to help someone if they are the same sex or opposite sex as you? There might be some issues there. What about the age of the person? If the person is the same age as you, or if they're 20 years older than you, or if they're a child, are you more or less likely to help them? What about race? Does that factor into it? All of these things could be things that actually do factor in to your likelihood of helping another person. I'm not saying that my participants are sexist or racist or ageist or any of these kinds of things, but nevertheless, those are possibilities that exist. And if I'm interested in studying those things, then those would be variables that I would want to manipulate in a different experiment, right? But the point is that those would be variables for a different experiment, not this one. This one, I'm trying to study the presence of bystanders. So that means I have to be concerned about that. And I need to make sure that my person A is always available to be the same actor, the same confederate in all of my conditions, because otherwise I've introduced what's called a confound, right? How can I be sure that if I really have a different actor for the 0 bystander case and the 15 bystander case, that if I have 2 different actors in those conditions, that my participants' helping behavior is really a function of the bystanders, or is it a function of the some characteristic of the confederate? And I don't know that. There would be no possible way for me to tease apart those 2 findings, and I would be left to be completely unsure. What's the real cause and effect relationship here? It could be the bystanders, but it could also be some characteristic of the confederate. And there could be all kinds of other things that might be going on that could influence the behavior. So what we have to do here when we talk about control, and that's my major bullet point there at the top, is control the situation. By control, I'm talking about not just my control in manipulating the independent variable in terms of how many bystanders are present, but I'm trying to also control the situation to make sure that all of the other possible factors that might be influencing subjects' behavior need to be held constant across all the conditions, so that the truly only different thing that is experienced by different participants is how many bystanders are there, and everything else is identical. And it's only in that case that I could really be sure that I have successfully isolated the independent variable and dependent variable and the relationship between them. And I can study that relationship. And that's what we said before is the goal in this study, is to isolate that relationship. Everything else has to be controlled for. And if we don't, we would say that we have an experiment that is not valid, right? What we're talking about here is what's called the internal validity of the experiment. I've probably at some point should have gone ahead and went to this particular screen, because this is kind of setting up the whole situation, is that my confederate's going to walk past them and drop their books and papers, right? And our manipulation is going to be how many bystanders on up, and then observe and record likelihood of helping, right? But as we have gone through here, all of those possible extraneous variables that we're concerned about need to be controlled for. Our goal is to isolate this cause and effect relationship that we think exists. That's our hypothesis. The hypothesis may or may not be true, but we will find out once we have our data, assuming that we have successfully controlled the situation. So as we had mentioned, that's called internal validity. That is, if I can truly conclude that the independent variable causes the dependent variable, and I've ruled out other possible explanations, that's a valid conclusion only if I have successfully designed the experiment. Let's have a look at another one. One that maybe doesn't involve the complexities of social interaction. Now it's just going to be a simple memory study. And I have a prediction here that arousal improves cognitive function and therefore improves memory. So there's a cause and effect implication here that if I increase arousal, I should be able to increase memory function. And if I were likewise to decrease arousal, I would decrease memory function, right? So we need our operational definitions of our variables. What do I mean by arousal, right? So again, arousal is something that I can't necessarily observe inside the mind of another person, but I can operationally define it somehow. Now, I previously talked about operationally defining things in terms of measurements, right? So I could somehow measure arousal in a person by hooking them up to some sort of a physiological device, such as maybe EKG to measure their heart rate, um, or a blood pressure cuff to measure their blood pressure. And those things can measure arousal. Not just heart rate, but there's actually some more complex measurements that come from physiology. Something called heart rate variability is a common measurement that we have used in our laboratory to measure our participants' arousal in various situations or stress levels. So heart rate variability refers to not just whether your heart rate is high or low, but does it change over time, right? So it's not perfect. Even if your heart rate, for example, is 100 beats per minute, it's not really a perfect exact 100 beats per minute. There's some random variation there. And as it turns out, variations in that heart rate over either small time scales or long time scales can tell us something about your stress levels. So, but we're not going to do that. Another way to actually operationally define arousal level is to manipulate it directly. And we can do that by administering something that we know causes arousal. In this case, it could be caffeine. So I can make sure that people who come in to the experiment have not had any caffeine that day. And then I can say that, okay, if you're assigned to be in the one condition where you get 1 cup of coffee, or maybe that's my example that I've written here, maybe I'm concerned about consistency of the dosing with coffee, and maybe I give them a caffeine pill, but the idea is I'm going to give them some kind of dosage. And so I know that if they've just had the 1 cup of coffee, that's how much caffeine they had. It's just that amount and nothing from before, right? So my dependent variable would be now memory, and I need to come up with an operational definition of that. So I need to come up with a memory test. It could be something, like we talked about savings times before, but let's just go with something simple such as percent correct on a memory test. I'm going to give them a list of things to memorize, and I'm going to let them study it for a period of time, and then I'm going to take it away, and I'm going to ask them to reproduce the list. I can measure their percent correct, right? So here's how I'm going to do the manipulation. I'm going to manipulate the arousal. I'm going to manipulate that through dosage of caffeine in coffee. So I'm going to have people drink 1 cup of coffee. Presumably it may take some time to have the effect, so I'll let them wait 15 minutes. Then I'm going to give them a memory task, which will be a string of random numbers. And they look at the numbers for 30 seconds. And then I take the numbers away and ask them to write down those numbers in the exact order. And they do that maybe 15 times. So then I'm going to do this again with a different group of people. And I'm going to give them 2 cups of coffee instead, and then do the exact same thing. And then again, I'm going to do this to another group with 3 cups and another group with 4 cups. And maybe at this point, we've reached our maximum dose. Hard to drink much more than that. Maybe. And let's say we do this experiment and this is what we get. So this is our actual data, all right? The number of items recalled out of 15 trials, or percent correct out of 15 trials, something like that. We get a graph that looks like this. So the 1 cup group remembered 8 out of 15. Graph doesn't go to 15, but let's just assume that that's the maximum that you could do. The 2 cup group remembered on average about 10 out of 15, and the 3 cup group got about 13 out of 15. And then beyond that, performance starts to decline, and we see that performance declines down to 9 out of 15 for the 4 cup group, and even a 5 cup group got 6 out of 15. And we can look at this and we think, well, that's an interesting pattern. And what it tells us is that our hypothesis was only partially true, right? Maybe. Because what it tells us is that as we increased arousal from 1 cup to 3 cups, performance did improve. But then as we went beyond that, performance started to decline again. And we might be left to conclude a couple of things, right? Which is that, well, maybe I've got a new and more interesting understanding of human behavior here, that there's maybe an optimal arousal level, and that at lower levels, 1 cup and 2 cup, performance decline, but there's also the possibility of too much arousal, right? Which might be the fine distinction between arousal and stress. And so once you go into the 4 cup, 5 cup territory, now you're starting to feel stressed, and that actually declines your performance, decreases your performance. But is that really a valid conclusion from this? One thing that we might notice here, let me go to the next thing here. Actually, I probably didn't even talk about it on that slide. So sorry to jump around there. But there's something that's pretty blatantly missing from this, and maybe you're guessing it. This is one of the unfortunate limitations of us being pre-recorded and not having a live class, because I would ask the class at this point, what's missing? And hopefully someone would guess that we're missing what's called the control group, right? We don't have a situation where there's 0 cups of coffee. So what we need to understand is the difference between a control group and an experimental group. So an experimental group is a group that actually receives some treatment or intervention that we are introducing, which this case would be the actual caffeine administration. And in fact, there's 5 experimental groups because there's 5 levels or 5 doses of caffeine. But a control group is there to show us what does performance look like in the absence of caffeine. And we might infer from this graph that it might be somewhere down here, maybe around 7, right? That seems to be, if I just were to extrapolate that line on down, that I would assume 0 cups would be down here, which mathematically is fine, but is that in fact reasonable without actually having done the 0 cup condition? What if our 0 cup condition was up here around 14 or 15? That would fundamentally and drastically change how we interpret these findings, right? It would imply that if our 0 cup condition was 14 or 15, that all caffeine administrations are bad, some though worse than others. And why 3 cups is somehow better than the others wouldn't make any sense anymore if 0 cups led to super high performance. So that is important, right? It would change drastically whether or not 0 cups is down here around 6 or 7, or even down here, or way up there, right? And of course, we can't know that unless we actually run that condition. So we're going to have to run that condition for starters, of course. But let's think about some other things that we want to be concerned about here when, again, goes to the issue of what we're calling extraneous variables and other aspects of the participant that we have to worry about might be influencing their scores on the memory test. What kinds of things might influence scores on a memory test besides just your arousal level and caffeine ingestion? Well, what about individual differences in memory skills? That's something that's true, right? These are called traits. And so one of the things we have to realize here is in psychology, we are concerned about two aspects of behavior, traits and states, right? They rhyme, so that's nice. Traits and states. There's a difference between them, of course, important. Traits are things that we would consider, as I've labeled here, enduring and stable. That means that a trait is something that's consistent about you. Your personality traits, talked about them before. Here again are the 5 personality traits that we think everyone has: openness, conscientiousness, extroversion, agreeableness, and neuroticism. Those are supposed to be things that are fairly stable about you. If you are a conscientious and agreeable person, I would expect to observe that in your behavior most of the time over long time frames, right? It endures. It's just who you are. It's consistent. Your intelligence or IQ, likewise, could affect your memory performance. And again, that's something that endures and it's part of who you are. It's stable. And likewise, then your memory function might be just some aspect of your overall cognitive capacity. It might relate to your intelligence, perhaps. Note under personality traits that I underlined conscientiousness, because that's a trait that could affect your performance in this experiment. Because a conscientious person is a person who says, you know, when I'm given a job to do, when I'm given a task, I'm going to do a good job and I'm going to put in my effort and do what's expected of me. And so if you're conscientious and you sign up for a research study as a participant and you show up and the experimenter gives you some instructions, you're going to say, okay, it's important that I follow these instructions and do a good job. That's a conscientious person, right? So these kinds of individual differences, high IQ, high memory function, high conscientiousness, maybe some other personality traits, could all affect performance on the test. States are different because states come and go, right? They're transient. And so It's possible, for example, that your arousal level is a state, and that we've induced that transient state with the administration of caffeine. But what about how much sleep you got? I said before that we'd want to make sure that our subjects are not coming into the lab having already consumed any caffeine, but uh, I'm not necessarily controlling for how much sleep they actually got the night before. Did they stay up all night and they get 2-3 hours sleep? Did they go to bed early, get 8 or 9 hours sleep? Who knows, right? Unless I'm asking and controlling these things, these are our these are aspects of my subject's states that that might affect them. And what's going on with their mood? Are they in a good mood today? Are they in a bad mood today? Um, are they preoccupied because of something that's causing them stress, that's interfering with their concentration because they're worried about their grades in a class, they're worried about a relationship, they're whatever, right? But there could have all kinds of things going on inside their mind that makes it difficult for them to concentrate on this memory test that they suddenly find themselves in, and they're like, I really don't care about this memory test right now because I'm worried that so-and-so is going to break up with me, right? Well, if that's the case, then their scores are going to decline on that test because of that, and not because of whatever caffeine that they have ingested in the experiment. So there's all kinds of things that could actually affect people's behaviors here. So one of the things that we have to do in order to deal with this, one thing that we could of course do is measure these things. I could give people IQ tests, and I could give people personality tests, and I could include in my questionnaire of demographic stuff at the beginning, how much sleep did you get the night before, and what is your mood today, and all this kind of stuff. And I could get all of these things and measure them all, and then I could try to ensure that I equally and evenly distribute these individual differences across all of the conditions. And so that way, if I come back here to my graph and say, okay, I have measured all of these things that I think could affect people, and I have ensured that my 1 cup condition has an equal number of people who fit the different categories, as does the 2 cup, 3 cup, 4 cup, and 5 cup, and I've got them all evenly distributed, right? But there's a few problems with that. It's very difficult to do all of that. It could take an hour to administer an IQ test, and then 30 minutes to give the personality surveys and all of the other surveys that I need. It could take 2 hours, 3 hours to do all of this kind of stuff right up in front. Suddenly this becomes a completely problematic experiment. And of course, what's also problematic there is not just how difficult it is to try to do all of this stuff in advance of the actual, here's the caffeine, here's the memory test part of the study, but there might be something about this 2 hours of survey taking and measurement that fatigues people. And now I've done something else that's going to have an effect on them that was not expected. And so really becomes an issue here. And of course, it also assumes that I'm able to correctly identify all of the relevant states and traits that need to be measured and distributed. And another issue here is that if I'm really going to ensure that I can evenly distribute all of the states and traits across all of the many conditions of my experiment, I might need to have a really, really large sample size. And by really, really large, I might mean hundreds and hundreds. I might need 500, 600 people. And if it's going to take me 3 hours to do an experiment and I need 600 people to do it, I'm going to be doing this study for months and months and months. And well, of course, that's the nature of science sometimes, is that we may have to go through all that stuff, but this becomes quite unfeasible. And so we do something else, and we take advantage of the laws of probability and statistics. So what we're going to do is we still want to have a fairly large sample size, of course, as large as we can reasonably get. But one of the things that we want to do is we want to try to randomly sample from the population, so that any person in the population who's out there and may have various states and traits will only be randomly selected. So there will not be, hopefully, any systematic pattern of particular kinds of people. This is going to allow us to generalize from our sample of subjects to the rest of the human population out there. And then what we're also going to do is we're going to ensure that we randomly assign our subjects to different groups. And so through true random assignment, we're going to ensure that whatever typical states and traits a particular subject has, that they're not all going to end up, it's not going to be the case that all of our highly intelligent or good memory functioning or good conscientiousness or good mood people all end up in the 3 cup condition, right? and that's crucial. So that way we don't have any systematic distribution of traits and states into a particular condition, such as the 3-cup group. And that's going to enable us to conclude, okay, the fact that the people in the 3-cup condition did better than everyone else is not because of their states and traits, it's because of their caffeine dose that they received, right? So what defines a large enough sample size? Well, statistics, there's ways in statistics to compute that. It's called a power analysis, and it enables you to make some assumptions about the magnitude of the effect that you're going to observe in the experiment, and it will calculate how many people you need to have in your sample to be considered large enough to be statistically reliable. And we don't need to worry about the mathematics of that for our purposes, but just know that it is possible to calculate these things, and that in the end, when we actually do statistical analysis, one of the things that we do is called inferential statistics. And what this allows us to do is it allows us to determine some aspects of the probability of observing this particular pattern of results. And when we say that results are statistically significant, what it means is that there's a certain degree of improbability associated with the findings. And we think that, okay, if this difference right here of the 3-cup group being much larger than the others is considered statistically significant, what that allows us to conclude is that that's an improbable enough finding that if it's really the case that there's no effect of caffeine, that we would not be likely to observe this. So we're left to conclude that there probably is an effect of caffeine on memory performance. Let's one more time consider the possibility that we'd be concerned about some other extraneous and confounding variables. So how are we actually doing this study? We might also be concerned about what time of day we're testing people, because that certainly has an effect on your background arousal level, background, resting level. What time of day do people perform best? We might think that people's arousal levels and cognitive abilities might vary throughout the day, and their memory skills might vary throughout the day. And let's say maybe 1 p.m. is a time of day where most people actually are performing their best, especially college students, perhaps young adults who taking classes and so forth. And maybe 1 p.m. is the best time of day. I don't know. I'm just making that up, but that seems reasonable enough. But let's just assume for the minute that that is the case. And let's say, for example, that when I'm doing this experiment, the most convenient thing for me to do is to get to the laboratory bright and early and start brewing up my coffee. And I'm going to have my first group come in, and they're going to get their 1 cup at 9 o'clock, and I'm going to do the testing. And then they're going to finish their testing, and then I'm going to send them home. And by the time the second group comes in, it's 11 o'clock, and they get 2 cups of coffee. And I do the testing and get everything cleaned up and ready for the next group at 1 o'clock, and they get their 3 cups of coffee, and so on and so forth. And I keep repeating this throughout the day, gradually increasing the dosage so that the people who come in at 5 o'clock are getting 5 cups. Well, as you can maybe imagine here, that now when it comes to figuring out why did the people who received 3 cups of coffee do so much better than everyone else? Is it because they got 3 cups, or is it because they were tested at 1 o'clock? So I could remake the graph. And in this case, I've changed the x-axis, right? Instead of the three cups of coffee leading to the highest rate of performance, maybe it's the 1 p.m. testing time that leads to the highest rate of performance. So this is exactly what we mean by a so-called confounding variable, right? The confound here is that caffeine administration and time of day have co-varied with each other. As caffeine administration changes, time of day changes with it. And so therefore, when I observe changes in the dependent variable scores on the memory test, I'm left to conclude, well, which one is the cause of that? Was it the caffeine change, or was it the time change? And I simply don't know. It would be as designed. This experiment is impossible for me to tease apart the effect, right? I did not keep it constant, and therefore I didn't successfully control for that other factor. And we would say that this study is not valid. I cannot validly conclude that coffee has the effect that we think it might have, because time of day was confounded with it. And therefore, I don't know. It becomes an invalid experiment. Now, as I've said before, there's a various other things. So let's say we fixed all of our issues, right? That we're testing everyone the same time, same day, Tuesday at 9 a.m., let's just say, right? We can keep it all controlled for. And we have included our control group, right? So we needed to do that. We talked about that already. So we need to have that zero coffee group. But as you are setting yourself up to think about your discussion for this video discussion 3, there's another thing that we might need to be concerned about: the placebo group. A placebo effect is an effect that sometimes happens to people simply because they expect the manipulation that they are experiencing to influence them, even if it might not. So there's some sort of an expectation effect or power of suggestion. So let's just pretend for a second that coffee has actually no effect on people's behavior, but people think it helps them. So you drink some coffee, and even though it doesn't improve your functioning, you think it improves your functioning. And therefore, you're going to do better at whatever it is you're trying to do just because you had the coffee, not because it really helped you, but because you think it helped you. And if our subjects in our study think that way, then they might actually kind of, quote unquote here, subconsciously, I put that in quotes because we don't really know what that means, and that's a term that's not very scientific, but something about them is causing them to try a little harder. And they do better on the memory test simply because of the expectation that the coffee should help them. So in this case, what we have to make sure that we do is we have to have some of our participants receiving not just zero caffeine, the zero cup group, that's our control group, but people who are receiving coffee without caffeine. Because now the idea is that they're drinking decaffeinated coffee and they don't know that it's decaffeinated coffee. So if there's any possibility that just the mere act of drinking coffee could have this kind of influence on people because they expect it to, then we can find that by giving them decaf coffee without telling them it is. Because then if we find that the people in the decaf group do exactly the same as people in the zero cup condition where they don't drink anything, then we would say, okay, there's no placebo effect happening, right? Because if you get decaf coffee, it's the same as not drinking anything at all. And therefore, no power of suggestion, no subconscious influence, right? No placebo effect. But on the other hand, if people who are drinking 3 cups of decaf coffee do exactly as well as people who are drinking 3 cups of caffeinated coffee, that is, they score really high and do better than everyone else, we might say that all of the influence of the coffee is actually due to placebo. It's not actually arousal, it's just due to the expectation. If there's no difference in performance between the caffeinated and decaffeinated coffee consumption groups. Most likely is that there's going to be somewhere in between, right? So there's maybe a small placebo effect, meaning that people who drink decaffeinated coffee do a little bit better than the zero cup group, the true control group, but not nearly as good as the people who are actually receiving the actual caffeine, right? And that would say, okay, we've got 2 things going on here. We've got a little bit of a placebo effect, but there's actual an arousal effect kind of above and beyond the placebo, right? But it's important that you do that. That way you can actually measure that and figure out, okay, we've got all these things going on and we can observe it and we can measure it. Something else that we might need to be concerned about here is what's called the double-blind procedure. So of course, when I say that we're going to give some of the people in the study some decaffeinated coffee, but we're not going to tell them it's decaf, that's called a blinding process, because what we're doing there is that we're including that manipulation and the subjects don't know about it. And therefore they're blind to whatever they have received. Right? They're blind to the fact that they're in a placebo condition, that they're in a decaf experiment, right? The same could be true if you're testing things like antidepressant medication, for example. People might report improvements in their symptomology when interviewed merely because they think the pill is helping them, right? That would be another placebo effect for a brand new antidepressant. So of course you have to give some of your people a placebo condition just to make sure that that's not what's going on there. But you don't want to tell them they're in the placebo condition, obviously, right? So you don't want people to know. But the double-blind procedure is also the case that when you have to make sure that your experimenter does not know whether the subject has received caffeine or no caffeine. All right, so you have to have maybe 2 experimenters now. One experimenter is in charge of brewing up the caffeinated and decaffeinated coffee and giving the appropriate version to each subject, whereas the other experimenter is in charge of actually interacting with the subjects and giving them the memory test. Because you don't want something about your knowledge. If you're the experimenter and you know that this subject is getting a decaf, does that affect the way you interact with them? Does it affect what you say to them? You have to be very careful. That's another thing in psychology research, so that we have to be very careful how we interact with subjects when they come into the lab. There could be subtleties of our expectations. Since I'm the experimenter and I know what's going on in the study and I know what I'm manipulating and I know what subjects are expected to do, I could give off unintentional subtle cues that could influence people. And therefore that could affect their behavior and cause them to conform to my expectations in certain ways that support the experiment. And that becomes another confounding variable, right? So we want to make sure that our experimenter also doesn't know which condition the subject is assigned to, that maybe the subject drinks their coffee in another room entirely. So there's in another room, an experimenter is brewing up the caffeinated and decaffeinated coffee, giving them their appropriate dosage, and then sending them to the other room where the memory testing experimenter is. And the memory testing experimenter has no idea how much that person just drank, and whether it was regular or decaf. They just have to give them the memory test. And now there's no way for that experimenter to have any kind of effect on them because they don't know what condition that subject is in. Maybe that's less of an issue in a memory test where we might think that there's not much that the experimenter could do to actually affect their performance, but it's possible. But it certainly is more of a concern in something where things might be a little more subjective, such as testing an antidepressant. Because not only is we worry about the subject's expectation of the antidepressant affecting their perception of their own symptoms, but now the idea is that if the experimenter knows that a particular subject is receiving a placebo version of the antidepressant, and the experimenter now has to just interview this person and ask them about their symptomology and make a subjective judgment about whether they are really reporting that they're feeling better or not. That experimenter's knowledge of whether the person's receiving a real pill or a placebo could affect their subjective judgment of the person's report about that. And if that experimenter really wants this antidepressant to be effective, they might downplay some things that people in the placebo condition say. And that might cause them to then insert their own bias. The experimenter is then unintentionally inserts his or her own bias into the data collection phase. So that's the important thing, is we don't want the experimenter to know what the situation is either in these kinds of things. So that's the bigger picture here, is that we always have to worry about both experimenters coming into the study with their own bias and expectations about what's going to happen, as well as our participants coming into the study with their own bias. And that's why we sometimes have to withhold some knowledge here. We talked before in our helping behavior with bystanders about not telling them that they're being tested for that, because that's going to bias them, right? We have to tell them it's about something else. And so deception is something that is sometimes done in psychology research, though as students in PSY2012 who are going to, in some cases, sign up for studies, are you going to experience those kinds of experiments where there's going to be some deception? It's possible, though I should emphasize that it's very rare. In fact, we don't even have a lot of social psychologists I don't think we really have any social psychologists doing research in our department. And that's one of the more common areas where deception is used historically, is in social psychology. And we'll have a chapter on that topic and later on, and we'll talk about some of the more infamous studies that have been done primarily back in the 1950s and 60s and early 70s, like Milgram's obedience study and Ash's conformity study and Zimbardo's terrible Stanford prison experiment. Well, I'm not quite sure that Zimbardo's study actually used deception very much, but it had its own problems. But Milgram and Ash's obedience and conformity studies, those did use deception. But that stuff isn't really very popular anymore. Let's consider one last issue here. Let's say I have a new hypothesis, again, a cause and effect statement, and I believe that watching violent TV or maybe if you want to be more a little topical in 2020, violent video games causes children to become more aggressive or violent. So that's our hypothesis. We know the independent variable is your exposure to violent media, TV, video games. The dependent variable is actual aggressive behaviors. So we're going to do an experiment and we're going to manipulate it as best as we know, right? So we're going to have our control group to get 0 exposure. And then we're going to have various experimental groups that get various other doses of violent media, 5 hours, 10 hours, whatever we think it is, for some period of time that we think is long enough to have an effect, maybe 6 months. And now that we've manipulated this and we've controlled for everything in the way that we know how to control for it, right? Randomly assigning people of different traits and states into the different groups, trying to control everything we can think of. And let's say we managed to successfully design a really good internally valid experiment and we measure aggression at 6 months to see if we have an effect. Well, can we do that? Well, sure, we could do that, but is it ethical? Because what happens, for example, if we really get the effect here that children watching 5 or 10 hours of violent media every day for 6 months actually become aggressive little monsters? We've done something pretty bad here, right? We have harmed our participant. And that's something else that we have to think about here is we cannot do anything at all to a participant that might harm them. And oftentimes we think that means, oh, you can't give them some weird experiment medicine that's going to make them sick, or you can't administer really severe electric shocks to them that are going to be very painful, right? Sure, you can't do any of that kind of stuff, but even these subtle things, such as exposing people to images or media that might have long-term psychological effects, cannot do that, right? So this is not an ethical experiment because I can't randomly assign a child to turn them into a violent monster. So instead, we have to do something else. We just maybe will observe children. We'll just let them do what they would normally do and not manipulate anything, and therefore we're not doing anything to them. We're just going to observe their television watching behavior. At most, I have to get permission from their parents or their schools to get this data, and I also to get their data about their behavioral problems and their likelihood of being aggressive and whether they act aggressively or not, right? And what I can do now is that after having observed and measured how many hours per day they're exposed to violent media and how many aggression behavioral problems do they have, what I can now do is I can find I find a pattern that's consistent with the hypothesis. I find that the kids who are watching more violent media, violent TV, violent video games are actually also more aggressive. And maybe also getting into more serious trouble. Delinquency is when you get into legal criminal problems under the age of 18. Does that allow me to conclude that my hypothesis was true, that watching violent media causes children to become aggressive? And the answer that you might hopefully already know is no, right? Because what we have here is not a true experiment. And that's what we're starting off these notes with, was the idea of a true experiment. A valid experiment is when you manipulate variables and control everything else to isolate that relationship between the independent variable and the dependent variable. And we didn't do that here. We didn't really manipulate. We didn't randomly assign kids to be into different conditions here. They come into the they come into the study already experiencing their variables. That is, they just watch what they watch, right? And so now what we have is called it's called an observational study, because we're just observing, we're not manipulating and controlling. And secondly, the nature of the data that we end up with is called correlational data, right? Because all that we have is we have a bunch of variables that we have measured, and we can measure the correlations between them. And a correlation is a statistical way of calculating the association. Is one variable associated with another? If two variables are associated with each other, what that means is that when one variable changes, the other variable tends to change too. And so there seems to be some linkage between them. But what's the nature of that linkage? Is it causal? That is there some cause and effect relationship? Maybe, but maybe not, right? And that's the problem, is that we don't really know. So we got different kinds of correlations. For example, here, positive correlation means that the variables are positively correlated. It means their changes go in the same direction. So when one variable goes up, the other goes up. When one variable goes down, the other goes down, right? They go up and down at the same time in the same direction. Negative correlations are when the changes are opposite each other. So when one variable goes up, the other goes down, or when one variable goes down, the other goes up. So they seem to be moving in opposite directions always, but they're still linked to each other. So that makes it an important statistical relationship. It's just in the negative direction, opposite direction. The absence of a correlation, we would say there's no correlation, is that if one variable changes, the other stays the same or just changes randomly, right? So why is it that we cannot conclude cause and effect from this? So there's the adage that you probably have heard before, correlation does not imply causation, but why? Two explanations, right? One is the directionality problem. So if I have two variables, X and Y, and they're correlated with each other, does that mean X causes Y? Or does it mean Y causes X? Back to our violent media example, it could be the case that violent media exposure causes children to become aggressive, but it could likely also be the case that children who are already aggressive now choose to watch violent media. So in that case, the direction of the causality is reverse from what our expectation was. But what's also quite likely, and probably very likely in this case, is the presence of a third variable, some other variable. Here again, we talk about extraneous variables and confounding variables being an issue here. Some other variable we haven't taken into account could actually be the simultaneous cause of both of these things, right? Something about the child's family situation or personality that causes them to both be aggressive and to both watch violent TV, but there's no direct linkage between those two things. They're both instead linked by this intermediary variable, right? The video that you're going to be watching about correlational effects for, I believe that is this video discussion number 2, talks about this kind of stuff because it talks about the classic textbook correlation of ice cream sales and violent crime being correlated with each other. Does it mean that ice cream sales causes crime? Does it mean that crime causes ice cream sales? Not likely, right? But instead there's a third variable, right? Ambient temperature. Summertime heat increases ice cream sales, obviously, but it also increases violent crime because people are outside more often in the summertime, engaged in social interactions with each other, which increases the opportunity for this kind of interpersonal thing that could lead to violence and so forth. And also the idea is that heat sometimes increases frustration levels that could also play a role in aggressive behaviors. So that's the third variable, right? It's explaining both. And thus there's no direct relationship between ice cream sales and crime at all. Other examples here, there's a website dedicated to analyzing so-called spurious correlations. So a spurious correlation is one in which two variables are related to each other, when in fact there's no real meaningful relationship between them. Likely because of some third variable, but in some of these cases, it's hard to imagine that there's even a third variable that could explain these things, right? This might just be purely coincidence, right? So the fact that the number of people killed every year by venomous spiders, it correlates in such an interesting positive way with the number of letters in the winning word of the National Spelling Bee. That's a meaningless correlation, right? There's no reason that those two things correlate with each other, but it is a positive correlation because as we see, as one curve goes up and down, the other curve mirrors it by going up and down more or less at the same rate, right? They're not perfectly related, but that's enough for there to be a pretty consistently strong relationship there. And the same down here about people the number of people who drown by falling into a pool every year, and the correlation between that and the number of films starring Nicolas Cage in a given year, right? Why does that correlate? Again, there's no third variable to explain that. It's purely random, it's pure coincidence. This highlights though something, despite the humor in these correlations, it highlights something that we do need to be concerned about because in psychology, there's a lot of variables that we can't easily manipulate or we cannot ethically manipulate. And we are left having to do this kind of observational research and dealing with correlational data as being the primary thing that we use to draw some conclusions about human behavior. And while we are always aware when we deal with correlational data that we know the limits in terms of reaching cause and effect conclusions, we still tend to look at the correlational data and to think, yeah, it's statistically significant, and that means it's it's improbable enough to assume that that's a real meaningful relationship. And even if we assume there's some third variable to explain it, we think that the relationship is still meaningful oftentimes when we're studying correlations in human behavior. But what these two spurious correlations and the others on this website, tylervigenvegan.com, URLs down there in the bottom right of each picture, what these tell us is that sometimes variables can be related to each other, and they really are correlated with each other, but they have no other actual meaningful connection. And so we would really have to be worried about that kind of stuff when it comes to observational studies of human behavior. We might find all kinds of interesting correlations that actually mean nothing at all. And that's just a cautionary note to conclude chapter 2. As always, let me know if you have questions.